I put together a theory about photons and electrons, and I took it to my physics teacher, who said it's not right.
Now, since he didn't describe the theory with great detail, I cannot answer, but I will say something that I forgot to say in the lecture. One has the advantage of using questions to finish the lecture. I must emphasize something that is a very great danger of talking about what happens in an experiment with one photon. Because after a while, you get the idea that these arrows are somehow associated with a single photon. It's a mistake, and I should have not permitted that mistake to be generated by mentioning as early as possible that it's not right, and that one of these amplitudes are not the amplitude to find a photon riding around somewhere, but the amplitude that an event occurs. And I give an example why your professor probably said no, by giving you a problem, so to speak, of the kind that we answer with these amplitudes, which is of a different style than the ones I've been mentioning, and requires more thought. And I would just at least, as I say, I don't know exactly what your theory is, and maybe it's okay to satisfy this example, but nevertheless, let me know next time. The idea is, suppose that we have a problem with two photons. Suppose that we would like to know, just to take a definite example, that we have two sources of light. Each one has been arranged, the two sources A and B, and it's been arranged that both A and B emit one photon under some circumstance, and you have two counters down here, two photomultipliers, and you would like to know what is the probability they both go off. All right? So the event whose probability you're computing is the probability they both go off at the same time. If they both emit, that there's a coincidence that they both go off at the same time. Now this has an amplitude, the amplitude for the two photons, so to speak. In one, there's only one amplitude, the amplitude that both go off. And I should have emphasized that no matter what the event, no matter how many you're involved with and so on, you talk about the complete event and calculate the probability of it, not the probability for each photon. Now in this case, to compute the amplitude for a photon, to both counters to go off, supposing that one photon came from each of the sources, it has to be done as follows. One way it could happen would be that this A source gave a photon that went off, and the B one gave a photon that made the other counter go off. Let's say this counter is called X, and this one's called Y. X went off because it received a photon from A, and Y went off at the same time because it simultaneously received a photon from B. The net result of the experiment is that both A and B have lost some energy, and the two counters went off at the same time. How do I compute that amplitude? Answer. You compute the amplitude that A would reach X from arrow. That's the amplitude A would reach X. You compute the amplitude that B would reach Y, another arrow. Actually very similar in this particular example because of the symmetry of the picture, but it's not relevant. What is the probable amplitude corresponding to the thing that both should happen? You can get a hint. Well, what the answer is the product of these two amplitudes in the same sense that I talked about before, multiplying. You're going to get an idea of why it's multiplying in this sense because of this. It helps a little bit. The time, if there's a certain chance that this reaches here, like 1/5 of them will reach here, and 1/9 of them will reach here, then the probability that they both reach is the product, and you've got to get that back into the amplitudes, and that's a clue. At any rate, you should multiply the amplitudes not only of things that happen in succession, but things that happen independently at the same time. This particular problem is especially interesting. Let's suppose when I multiplied these two, by the rules I'm talking about over there, I get add the angles and multiply the lengths. I get this answer. That's not the right answer for this problem, incidentally, and it's curious. Because there's another way it can happen. You're all sitting there saying, well, how the hell did I know that it wasn't A that went to Y and B that went to X? Well, if I say that this was, remember, this one was A to X, and that was B to Y. Now, if I say A to Y, that's a different arrow. Why? Because it's a longer and therefore different time, and therefore this particular arrow is turned more. And likewise, B to Y is turned more. I'm not drawing them correctly because there's a symmetry there that's similar. At any rate, the net result for that case is some other arrow for the other case. Now, what do you do when you have two possibilities? If a thing can happen more than one way, you add the amplitudes for the two ways. And the net result for this problem is to tie one of these arrows onto the other, and that's the answer, the length of that. And now what we have is something which is all the elementary textbooks say is impossible, interference between two photons. Or more correctly, you get pluses and minuses depending on the angles, strengthenings and weakenings, depending on the positions of these two counters relative to each other. This is used, as a matter of fact, and was invented, I think, locally. Perhaps not in New Zealand, but at least in Australia. To detect the diameter of stellar objects or quasars and things like that, by looking for radio waves received in two receivers and looking for correlations of strength, which just means a coincidence of photons. It's called the Brown twist effect. But it's a perfectly definite effect that's understandable and computable this way. Most people's theories, who have a theory about waves associated with photons, will not have a theory which is capable of dealing with situations where there's more than one photon. I do not know that your theory is incapable. I only suggest that as an interesting problem.
How old is this theory of quantum electrodynamics?
Present complete form is from 1948 or 7, 8. Therefore, it's 30 years old. That's what the subject of these lectures is. As you see, the reason it's so difficult to filter down is the resistance of your mind to such models. People who hear that all I'm going to do is make a couple of arrows on a board to calculate the chance that something happens, says this guy doesn't know physics. But this is the guy who knows that that's what you have to do and admits, therefore, that he doesn't know why he's doing what he does. And you can have the confidence that when I say I don't know what I'm doing, that probably nobody else does either.
In what way is your theory different from wave mechanics?
The question is how is this related to wave mechanics? Now, the reason I hesitate is there was a thing called wave mechanics, which is a quantum theory of wave theory. And there's also another sense in which we might be using the word the mechanics of waves, by that meaning water waves or sound waves or something like that. There's a special theory called wave mechanics, which is discovered and developed in 1926, which is just another name for quantum mechanics. And that there was two things. First, there was an equation for these waves, these matter waves, made by Schrödinger. And then there was an interpretation of these equations by Max Born within the year, which was that the function that we're talking about is a complex number whose square is a probability. I am saying no more than that at all. That's exactly it. The only thing I can add that for the 20 years after is merely a refinement or an improvement in discovering exactly how to calculate the wave amplitudes, or these numbers, these arrow amplitudes, for photon phenomena and electrical phenomena of high energy and so on. The complete formulas for quantum electrodynamics took 20 years to get straightened out exactly, and that was why I said 1949. But 99%, well, 97% of the thing was worked out in 1929, and the interpretational scheme about probability amplitudes and that you square them to get probabilities, which is so strange, is the resolution, shall we say, or a description, a precise description of what was, for a while, a confused wave-particle duality. You might say, but you still have a sort of a wave in the sense of something turning or oscillating, and the particle somehow in the sense of the particle going. So it's still a duality, but the words wave-particle duality is a description of a condition of the mind of physicists before 1926, in which it was best described as saying, it looks exactly like a wave, but that's on Thursday. And it looks exactly like a particle, but that's on Tuesdays. But the answer is it does not look exactly like an ordinary particle bullet with normal probabilities. And it does not look exactly like ordinary waves, because it ends up that you measure it in particles. And how to put that together? Answer, this is the way it looks.
Then in your own mind, do you think you have resolved this peculiar duality?
Not at all. I haven't done anything about it. The wave-particle duality represented a state of confusion. It was a word that there was a wave-particle duality. It was a phrase used to describe a state of confusion as to exactly what law to use to figure out what happened in each circumstance. Also a confusion of model, whether it's wave or particle. This thing, the final way out, worked out by Born, 1926, it's still got dual aspects of wave and particle, but it's precise in telling what to do and to predict the circumstances in any experiment. And is in agreement with with experiment. And so it's a resolution of the confusion, but it's not a resolution in the sense of producing a model which is clear, physical, in the old-fashioned sense of waves or particles.
Are the clicks from a photomultiplier caused by the photomultiplier and in no way related to light?
The question is, when a photomultiplier makes clicks, is it the photomultiplier itself that's making the clicks, or is it light? And the answer is, it's light, in the sense. And insofar as it's actually quite true that photomultipliers make clicks all by themselves in circumstances in which we've done everything we can to make it as dark as possible. In other words, it's dark, and there is no light. Various things it's because it's so extremely sensitive, and one can do things to the photomultipliers to improve it, such as cooling the cesium surfaces so they don't emit spontaneous electrons and so on, until we get an instrument, the idealized photomultiplier, which is better and better in the sense that it has less and less counting in the dark. But whether it has counting in the dark or not, when you change the circumstances, that in normal parlance, in ordinary language, we'd say light is coming in the sense that the sun was shining, but we put a whole lot of black paper around it, and we got a lowest count, make a hole in the paper, and all of a sudden the counts go up. In all those circumstances in which we would expect in ordinary language to say light is going in, and in all those circumstances the counts on the photomultiplier are increased. And the increase is by an amount that depends upon how much light is let in. The increase. If you improve the photomultiplier so the dark current is much less, you get the same number of excess counts due to making holes in the black paper. Because the circumstances in which the photomultiplier increases its count are those which are commonly associated with circumstances in which the common English use of the word light is used, we use the same word and say, when you have a situation that you would say light's going in, I'll guarantee you the photomultiplier will go off.
Is light then wave-like?
No, it's discrete. It always works discretely. Ah, yes, discrete. Because no other instrument has ever been designed or can be designed, if people have tried and they've argued about it and discussed it, whether I build a photomultiplier or any other instrument for the detection of light of low intensity, it always ultimately behaves in this pulse-like manner. I only use one example, but every instrument that detects light at sufficiently low intensity always ends up discovering that light comes in these lumps. Also, the behavior of light in many other circumstances, like in in hot regions and so on, Planck discovered that he could not understand many of the properties of the distribution of light from furnaces and so forth and other technical situations unless the energy of the light could not come in arbitrary amounts, small amounts like the wave theory expected, but had to come in definite lumps of a certain amount of energy depending on the color. And so it's all this, not just a photomultiplier, but all the other experimental situations and so forth, which it's impossible in a popular lecture without 4 years of study to produce and to demonstrate again and again all these experiments to produce the kind of conviction which one would get from a long experience. It's unfair of me to say you've got to believe me because there are all these experiments, but the best I can do then is to refer you to other books and stuff where experiments are reported of all kinds, which will show you that that's the way it looks. That's the best I can do.
Can your theory explain the redshift or blue shift of light from stars?
Yes. Yes, and that was a point that I was coming to, but I'll try to. Because of the time, I guarantee you, if you promise to come next time, which is next Tuesday, I will contain it. I had intended to put it in this lecture, but I saw that was one of the things I was coming to. The idea is relatively simple, and I'll try to explain it. The color of light has to do with the speed at which that amplitude turns around. I never talked about how the detector would look, or the photomultiplier would see if it was moving toward the source. But what happens is that the time that we're talking about to get the amplitude is always shorter as it approaches the source. And because of this changing timing from the motion on top of the rotating, it appears as if the arrow effectively at this multiplier is turning at a different rate. And that is equivalent to what would have happened to the multiplier if it's standing still, but the light source had a different color. And therefore, the behavior of an instrument which is moving toward a source is to react as though the source was standing still, or the object was standing still, but the color were bluer. All right? It's not very clear, but I perhaps make it better next time.
Right, but we must make a break there. I'm sure Professor Feynman needs all the time he can to get his next lecture.